Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Organic Chemistry Paper 2. In the 7th module, we are currently studying about acids and its derivatives. In the lecture 3, we will be studying about reactions of acid derivatives. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. Let us look at the topics that will be covered in this particular session. So we will be studying about reactions of acid derivatives, mainly the reactions of acid chlorides and the comparison between nucleophilic addition and the substitution reactions. We will also be studying about the reactions of acid anhydrides and the various hydrolysis reactions of acid chlorides, esters and amides. We will be studying about the base catalyzed acyl oxygen cleavage bimolecular reaction. We will also be studying about the importance of acid and base catalyzed alkyl oxygen unimolecular hydrolysis reaction. We will also be studying about Claisen condensation. Let us study about the properties and reactions of acid derivatives. So we will start our studies with the properties of acid chlorides. So acid chlorides, as we know, undergo nucleophilic substitution reaction faster than alkyl chlorides. So why do acid chlorides undergo nucleophilic substitution faster than alkyl chlorides? Let us see. So here this is the alkyl chloride, this is the acyl chloride. So we will now find out why this reacts slower compared to this one, or this reacts faster compared to the alkyl chlorides. The first reason is the attack takes place in the sp2 carbon for the acid chloride. So this is a sp2 carbon in the case of acid chloride, whereas it is a sp3 carbon in the case of alkyl chloride. Now we will see why this difference actually makes acid chlorides highly reactive. The next reason is the presence of electronegative oxygen pulls the electron towards itself, making this carbon more susceptible to nucleophilic attack. In other words, this carbon behaves more having delta plus charge because there is one electronegative oxygen, there is another halogen which is also electronegative. So both of them pull the electron towards themselves, making this particular carbon more electrophilic in nature. Whereas in the case of alkyl halides, there is only one halogen present, so it can only pull to certain extent. Even though it can make this R group little bit electrophilic in nature, unfortunately the acid chlorides carbonyl carbon is much more electron deficient. So these are all the two reasons. The first one is the electrophilic reason, is the steric reason, that is the bulkiness, that is the hybridization sp3, which is a tetrahedral structures compared to sp2, which is a planar structure. So the attack of the nucleophile is far easier when it is a planar one compared to a tetrahedral carbon. So that is the reason the steric effect plays a deleterious role in the case of alkyl chloride. So that's the reason they react slower. And when we talk about electronic effect, this carbon becomes more electron deficient because of the presence of two electron withdrawing substituents. So due to this reason, acid chlorides are highly reactive compared to alkyl halides. Now let us see the next important problem. We also have seen this earlier, like aldehydes and ketones generally undergo nucleophilic addition reactions, whereas acid and its derivatives undergo nucleophilic substitution reaction. So there is a huge difference between addition and substitution. Now we will see what is the reason for this difference. Let us look at the electronegativity of the various substituents that are attached to the carbonyl carbon. So here in the case of aldehyde, we have a hydrogen whose electronegativity value is 2.20, and in the case of ketone, there is a carbon which is attached to the carbonyl carbon whose electronegativity value is 2.55. In the case of carboxylic acid, we have oxygen. In the case of esters also we have oxygen, so the electronegativity of oxygen is 3.44. In the case of acid chlorides we have 3.16 electronegativity, and for amides the nitrogen is having electronegativity 3.04. So if you very carefully look at, the carbon is having 2.55, but all the other acid derivatives, they have an electronegative substituents which is much more powerful electron withdrawing nature than the carbon. So this is one of the clue. Let us look at what is this in the next couple of slides. So we will start from the electronegativity. So in the case of aldehyde, we know carbon is more electronegative than hydrogen. So if you look at the hydrogen's electronegativity, it is 2.22, and for carbon it is 2.55. So in other words, between carbon and hydrogen, actually the carbon pulls the electron towards itself more. That means hydrogen actually pushes its electron towards this carbon. So in other words, this particular carbon can now accommodate one more electronegative substance, basically the nucleophile. In most of the cases, the nucleophile is actually an electronegative element, so that can be added to this carbon. So what we are saying is it can be added. So remember, addition is possible in this particular case. In the case of acids, amide or acid chloride, what is the problem? In the case of acids, amides or other substituents, acid derivatives, we have one oxygen which is electronegative, we have another Z group which is the acid or other substituents. All of them are having higher electronegativity than the central carbon, so they also pull the electron towards themselves. This oxygen pulls the electron towards themselves, and finally the nucleophile also is basically pulling electron towards itself. So if addition reaction takes place, there are three groups which actually pull their electron towards themselves, making this carbon highly unstable. So that is the reason the nucleophilic addition reaction does not take place in the case of acid derivatives. Only nucleophilic substitution takes place. So let us compare the nucleophilic addition and nucleophilic substitution and confirm why acid and its derivatives prefer nucleophilic substitution reaction. Now, this is the nucleophilic addition reaction. This is shown by aldehydes or ketones. This is the nucleophilic substitution which is shown by acid and its derivatives. Here the Z is nothing but OH, halides, amides, esters, all the OR groups are the Z groups. Now, what happens in the nucleophilic addition reaction? In the case of addition, what happens is change of hybridization takes place. That is, this is a sp2 carbon which becomes sp3 carbon, because 4 it's a tetrahedral one. So there is a change in the hybridization in the case of addition. In other words, the molecule becomes more crowded after the addition. So if it is a hydrogen, it is a very small unit, so it can easily accommodate another nucleophile in its proximity. So that is one of the reasons aldehydes can undergo nucleophilic addition. Whereas in the case of substitution, what happens? The Z group is a bigger group. It may be oxygen or halogen or nitrogen. So when they are there, one more another nucleophile coming and attacking this carbon makes it more crowded. So the higher crowding also is not favored. That is the reason instead of addition, substitution takes place in the case of acid and its derivatives. As I mentioned, there is a change of geometry from planar to tetrahedral. When it goes from aldehyde or ketone to the nucleophilic addition product, there is a change of geometry. Because of the presence of a small hydrogen group, the change of geometry is accommodative in the case of aldehydes and ketones. In the case of ketone, there is a small alkyl group, so addition is possible in that case also. And here what happens, see this C double bond O becomes COH. So a double bond is getting converted to a single bond, whereas in the case of nucleophilic substitution, the C double bond O remains as C double bond O. In other words, C double bond O is retained. So whatever we are mentioning here is with respect to the reaction center. Okay. And another major issue is either hydrogen or the alkyl group is a very poor leaving group. So this is also one of the reason they stick to the carbon. They don't want to leave because they are not a good leaving group. So that's the reason they prefer addition. Whereas in the case of acid derivatives, we have OH group, Cl group or NH2 or OCOR. These are all better leaving group compared to hydrogen or alkyl group. So that's the reason they generally leave. That is the reason it prefers nucleophilic substitution. And in the case of nucleophilic addition, a new sigma bond is formed at the expense of a C double bond O, that is a pi bond. So one pi bond is converted into one sigma bond. New sigma bond is formed in this one, which increases the stability of the molecule. Whereas here, one sigma bond is replaced by another sigma bond. That means the Z group is the leaving group. Its bond is replaced by a new nucleophile and the carbon sigma bond. So as I mentioned, the star indicates it is at the reaction center. So all the change of geometry, hybridization, all this happens to the reaction center. So this is the reason aldehydes and ketones undergo nucleophilic addition, whereas acid and its derivatives undergo nucleophilic substitution reaction. So the carbonyl carbon is highly electrophilic due to two electronegative units. So because there is one oxygen which is electronegative, there is another X or Z group which is also electronegative. That's the reason this carbonyl carbon becomes highly electropositive. So this favors substitution reaction. And again, this is a sp2 or a planar hybridization, so less crowding is there. And another thing is X is a very good leaving group. So these are all the things we have already discussed. And when we look at the reactivity, the acid chlorides are highly reactive compared to acid anhydrides, which are better reactive than esters. Amides are the least reactive one. Now we will see the reactivity, why the difference in reactivity for the various groups. HCl can dissociate into H plus and Cl minus. Acid can dissociate into H plus and RCOO minus. Alcohol can dissociate into H plus and RO minus. Ammonia can dissociate into H plus NH2. So between all these reactions, this is much more facile reaction. In other words, this HCl can easily give out its proton compared to ammonia, because we already know ammonia is basic, so it doesn't want to give out the proton very easily. So if we have to put the acid strength of all these groups or all these compounds, then we can arrange them like this. the acid strength increases from ammonia to HCl. So HCl is a very strong acid. In other words, it can very easily give out H plus ions, whereas carboxylic acid is little bit having lesser tendency to lose the H plus ion compared to HCl. This is a mineral acid or inorganic acids. So generally many of the inorganic acids are having much more higher acid strength compared to carboxylic acids. And when we look at the basic strength, ammonia is strongly basic compared to HCl. So that way ammonia does not want to give out H plus ion, whereas HCl wants to give out easily the H plus ions. So from that, let us look at the relative reactivity. So that means when we have a Cl minus, that is a very good leaving group, and when we have NH2 minus, it is a very poor leaving group. So that way we can compare, like acid chloride is highly reactive, followed by anhydride, followed by esters, and amides are the least reactive one. So from the acid strength or from the basic strength, we can easily compare why chlorides are easily removed from the system. Let us look at the reactions of acid chloride. The first one is hydrolysis of acid chlorides. So in this particular case, acid chloride can be hydrolyzed to carboxylic acid. We will now look at the mechanism, how the reaction actually proceeds. So in the reaction medium, there is plenty of water molecules. Oxygen is having a lone pair of electrons. So this carbon is a electrophilic carbon, that is electron deficient. Because of the oxygen's present, the electrons are pulled towards itself. So the initial step is the attack of the lone pair of electrons on the electrophilic carbon. We will see the step by step how it proceeds. So the initial step, this oxygen carbon bond is formed. Oxygen becomes now oxonium ion is formed. This is quite unstable, so it pulls the electron between O and H bond. The bonding electrons are pulled by the oxygen. So by the loss of H plus ion, we get this particular intermediate. So this intermediate is quite unstable, and chlorine being a very good leaving group, that pulls the carbon halogen bonds electron towards itself. So to compensate the loss of electrons on the central carbon, the minus charge on the oxygen is shared between carbon and oxygen, so that forms a double bond. Now the loss of Cl minus produces carboxylic acid. So this is how the reaction actually proceeds. And there is a chloride ion, there is a H plus ion, so these two combine together to form HCl. So if acid chloride is treated with a carboxylic acid, we end up with the corresponding anhydride. Let us look at the acid-catalyzed hydrolysis of acid chlorides. So in this particular case, what happens is, initially we have a H plus ion in the medium. So always we had seen earlier also in the electrophilic addition reactions, always the H plus is added to the electronegative oxygen. So in the case of aldehydes and ketone also, we had seen the similar reaction also occurs here also. So the oxygen takes the H plus ion and it becomes the oxonium ion. So this oxonium ion is now being attacked by the solvent water molecule, because there is a lone pair of electron on the oxygen, and this carbon is electrophilic in nature. This oxygen pulls the electron towards itself, so that the charge is neutralized here as a OH it becomes, and this oxygen, since it lost the lone pair, it becomes oxonium ion. So as usual, this OH bond is broken and the oxygen takes away the electrons, leading to the loss of H plus ion, gives this particular intermediate. So in this case, there are three electron negative elements are present on this particular carbon. So that's why this is quite unstable. and the bond, this oxygen hydrogen bond is broken and this chlorine is lost, as we had seen in the previous case also. So this leads to the corresponding carboxylic acid. So this is how the acid catalyzed hydrolysis of acid chlorides happens. And in the case of base catalysis, the base first adds to the electrophilic carbon and we end up with this particular intermediate. So this intermediate actually loses the chlorine to produce the corresponding carboxylic acid. So this way acid chlorides undergo either acid catalyzed or base catalyzed hydrolysis to produce carboxylic acids. Then let us look at the reduction of acid chlorides. Acid chloride can be reduced by lithium aluminum hydride followed by acid treatment to give primary alcohols. Even sodium ethanol reduction of the acid chloride also produces primary alcohols. Acid chlorides using Rauschenmund reduction, that is pelletized barium sulfate, gives aldehydes. Or acid chlorides when treated with the dibal H also produces aldehydes. So these are all the two ways how the acid chlorides can be converted to primary alcohols or aldehydes by reduction. The next reaction is the reaction of acid chloride with alcohol. So acid chloride when treated with alcohol produces esters, and with the sodium salt of the alcohol also they produce esters. So these are all the two reactions of acid chlorides. And acid chlorides when treated with ammonia produces primary amide. Acid chlorides when treated with amines produces secondary amide. And acid chlorides on treatment with the secondary amines produces tertiary amides. So these are all the various amides which can be produced by acid chlorides. And the next one is the Friedel-Crafts reaction. So the Friedel-Crafts acylation of aromatic systems in the presence of AlCl3, that is a Lewis acid, produces acylated benzenes. And the reactions of acid chlorides with the Grignard reagent produces ketones as the first product. If we are using excess of Grignard reagent, then it leads to the formation of tertiary alcohols. So in this particular case, there are two alkyl units which come from the Grignard reagent. Whatever is the alkyl magnesium halide, whatever we are using, they both are introduced into the tertiary alcohol. And acid anhydrides when treated with ammonia, they also react very similar to acid chloride. The only difference is anhydrides react slower compared to acid chlorides. So anhydride when treated with ammonia produces primary amide. Treatment of anhydride with amines produces secondary amides, especially alkyl amines. Anhydride when treated with the secondary amines produces tertiary amides. Similar to acid chlorides, anhydrides also react with Grignard reagent to give ketones, and if we use excess of Grignard reagent, they also lead to the formation of tertiary alcohol. So in reactivity wise, acid chlorides and anhydride, they react very similar. The only difference is acid chlorides are highly reactive compared to acid anhydrides. Let us look at the reactivity of acid chlorides. So now we will study about the acid catalyzed alcoholysis of acid chlorides. So now you will be confused, what is this acid and what is this acid? This acid is a aliphatic or aromatic acid chloride, and this acid is a mineral acid which is an inorganic acid, and this is an organic acid chloride. So in most of the cases, mineral acids are a very good catalyst for organic reactions. So here in the first step, an acid chloride is treated with an acid. So this, as we have already seen in the Fischer esterification reaction, the steps are going to be more or less very similar. So the initial step is the the lone pair of electron from the oxygen is given to the H plus ion to form a OH bond. So due to that, the oxygen develops a positive charge or an oxonium ion is formed. This particular carbon becomes more electrophilic because there is a positive charge on the electronegative oxygen, so this is quite unstable. So obviously this oxygen will pull the electron towards itself. So due to that, this particular carbonyl carbon becomes electron deficient, and the lone pair from the alcohol oxygen is given to this electrophilic carbon, which forms a CO bond as shown here. So we have the alcohol molecule getting attached to the corresponding acid chloride. So this intermediate is formed. In this particular intermediate, this oxygen is having a positive charge, so this is the oxonium ion. And now this being quite unstable, it loses a proton to give the stable intermediate. So this intermediate has 3 electron withdrawing or electronegative atoms on the central carbon atom here. There is an oxygen, there is a halogen, there is another oxygen. So 2 electronegative oxygens and 1 electronegative chlorine are there on this particular carbon. So this is quite unstable intermediate. So this, on the chloride being a very good leaving group, it is going out as a Cl minus ion. To compensate the loss of electron on the central carbon atom, this OH bond is now cleaved, and the electrons from this OH bond is now given between carbon and oxygen bond. So that leads to the ester as shown here. So this is how an acid chloride is converted to corresponding esters. Although this is an acid catalyzed reaction, even base catalysis is also possible for the formation of esters. Now let us look at how the base catalysis works. So here the acid chloride is treated with the alkoxide anion. So this alkoxide anion is having a negative charge. This carbon is electrophilic in nature. So this negative charge is given to this particular carbon, and this leads to an intermediate where oxygen is having a negative charge. This is very similar to an intermediate which we have seen here. This particular carbon is having 3 electronegative units. So one of the unit has to be removed. So chlorine being a very good leaving group, the charge reversal leads to the loss of chlorine atom. So we end up with the corresponding esters as the product, and the Cl minus is removed. So how the OR minus is formed is basically we need a strong base. A base should be much stronger, and then only it can abstract a proton from the alcohol. So the initial base abstraction of proton from the alcohol produces the alkoxide anion. So this alkoxide anion is the one which is actually responsible for the attack on the acid chloride. Alkoxide being a very strong base and a nucleophile, a hydroxide ion cannot abstract a proton from the alcohol to produce the alkoxide anion. So in this particular case, sodium ethoxide or a very strong alkoxides are used to initiate this particular reaction. The hydroxide base cannot be used for this base catalyzed reaction. So even though this reaction we say base catalyzed, the hydroxide ion is not the base which can be used for this particular reaction. We need to use a much stronger base. Then only this reaction proceeds. If we simply use a hydroxide ion, then what will happen? Simply what will happen is this chloride will undergo exchange. In other words, we will end up with a carboxylic acid as the product and not the required ester. So whichever is the nucleophile that is present in the system will add to this particular electrophilic carbon. If it is a alkoxide, we end up with a carboxylic ester. If it is a hydroxide, we will end up with a carboxylic acid. So the nucleophile which is added is very crucial for this particular reaction. Let us study about ester hydrolysis. So this is basically a BAC2 mechanism which we are going to study now. So what B refers to is the reaction is a base catalyzed reaction. Now AC means acyl oxygen bond is cleaved in this particular reaction, and 2 means it's a bimolecular reaction. So what is this reaction we are actually going to see? We have a carboxylic acid ester as shown here. So we have two ways of hydrolysis. We will see both the different types, how the reaction can actually undergo hydrolysis. The first one is the oxygen and the R prime bond can be cleaved as shown here. So this is a oxygen alkyl group bond cleavage. So this is what is called Al. So Al means basically alkyl group. The bond between oxygen and the alkyl group is cleaved, so this is represented as Al mechanism. And there is also another way by which the ester can be hydrolyzed. So here there is an acyl unit here, there is an oxygen here. So the bond between this particular carbon and the oxygen can also be cleaved. So this is what is called acyl group and the oxygen cleavage. So in other words, it is a AC. So we are going to study about this particular AC one. That means acyl oxygen bond cleavage is the reaction we are actually going to study. Now we will have to find out why we say it is a acyl oxygen bond cleavage and not the alkyl oxygen bond cleavage. There are various evidences which points to the acyl oxygen bond cleavage. We will see one by one evidence to confirm that the ester hydrolysis by the base catalyzed reaction is a acyl oxygen bond cleavage reaction. We will confirm with various evidences. So in the case of esterification of carboxylic acids, the ester oxygen came from alcohol. From O18 studies, people had actually shown that the oxygen of the ester came from the alcohol unit. So this one we have studied earlier also using the O18 studies. When we studied about the formation of esters, we have seen this particular reaction. So we will study now about the BAC2 mechanism. So using the kinetic studies, it was confirmed that the rate of the reaction depends on the concentration of the ester and the base. So there are two species which are involved in the rate determining step. So that is why this is a second order kinetic. So we can say it is a bimolecular reaction. Now we will have to look at how we confirm this is a acyl oxygen bond cleavage. So we can study using the stereochemistry. So we have a starting material. We have one R group that is attached to the carbonyl group. There is another R prime alkyl group which is attached to the oxygen. So if it is a acyl oxygen bond cleavage, that means this bond is cleaved, then the stereochemistry of the R group has no effect on this particular reaction. In other words, the R group is not at all affected because it is not involved in the bond breaking. So the stereochemistry of this group is not at all affected. So we cannot use the stereochemistry of this R group to study or confirm whether the acyl oxygen group is cleaved or not. We cannot confirm. So what is the next one? If we look at R prime, if the R prime is affected, that means if the alkyl oxygen bond is broken, then we will end up with the inversion in configuration. So this is the alkyl oxygen. So if the alkyl oxygen bond is broken, then we end up with the inversion. R prime is not affected means if the if this acyl oxygen bond is broken, then we will end up with the retention in configuration. In other words, if this bond is actually broken, then this RO bond remains intact. So that means we will end up with the retention in configuration. If the alkyl oxygen bond is broken, then the nucleophile will come and attack from the opposite side, which leads to inversion in configuration. So that way we can confirm whether the alkyl oxygen bond is cleaved or acyl oxygen bond is cleaved. We can confirm alkyl oxygen bond cleavage. So let us take one particular example, which is a stereochemical one. As we mentioned, this R group stereochemistry is not at all affected because that is not involved in the bond breaking during the ester hydrolysis. Only this particular bond or this particular bond is cleaved in the reaction. So we will now study the stereochemistry change of this particular carbon to confirm how the reaction actually proceeds. We can start with the secondary butyl alcohol. This is treated with an acid to give the ester. So the secondary butyl alcohol is this part. So this part is the alcohol is this one. So we have a known configuration, that is the plus isomer is taken. So this is now converted to the corresponding esters using treatment with acid. So now the ester can undergo bond cleavage. So let us say we have a CO bond cleavage, that is this carbon and this oxygen, this particular bond is cleaved, then we will get inversion of configuration. So that means the OH minus will come and attack this carbon from the opposite side of the cleavage bond. So in other words, this oxygen will now go with this unit. So this side it is going to be empty. So to compensate that, the nucleophile has to come and attack from the opposite side. So that leads to inversion of configuration, because in the initial starting material the CO bond is present. Say for example, in this particular case I say it is on the left hand side, but in the product we are going to get on the right hand side. So that means there is an inversion of configuration happens if CO bond is cleaved in the hydrolysis step. So what is the other one? We can also have the AC, that is the acyl oxygen bond can be cleaved. So that will lead to another product which is going to have the retention of configuration. So that means if this carbonyl carbon and this oxygen bond is cleaved, the nucleophile will come and attack from this side. That leads to retention of configuration because the O minus, that oxygen is cleaved from this side only. So in the same side the OH is going to come and attack. So we are going to get a product. That means our final product is going to have the hydroxide unit from this unit only, because when this particular bond is cleaved, we don't mind from which direction this OH comes and attacks, because this carbon and oxygen bond remains the same, because the stereochemistry of this carbon and oxygen bond is not at all affected if this O and C acyl bond is cleaved. So in other words, the OH group which is present in the left hand side of this intermediate, that is the ester, will be retained in the final product, the alcohol. Okay, so after the hydrolysis, this OH will remain on the left hand side only. So we will end up with a retention of configuration. So by this we can actually confirm which is the product that is formed. So from the secondary butyl alcohol studies, it was shown that the final product after hydrolysis is having a plus configuration. In other words, retention is the one which is observed. In other words, we can say the bond cleaved is between the oxygen and the acyl unit. So this is one way of confirming the acyl O bond cleavage happened using stereochemical studies. So the next one is isotopic labeling studies. So in this particular case, we are starting with an ester which is O18 labeled. So this is the starting material we are using. So this undergoes hydrolysis using base. So this leads to an intermediate A. We already know how this intermediate is formed. So this OH is having a negative charge. So this is the nucleophile. This is the electrophilic carbon. So this OH minus comes and attacks this carbon, and this bond is now shifted. The carbon oxygen double bond is shifted towards the more electronegative oxygen. So this labeled oxygen now has a negative charge on it, and the OH is added to the central carbon. So we know this is a quite unstable intermediate because there are 3 electron withdrawing oxygen are present on this particular carbon. So one of the group has to leave. In that case, the OET group is lost to give the corresponding carboxylic acid. As we have earlier also studied, even the added OH nucleophile can also be cleaved in this particular reaction, but then that actually simply prolongs the reaction. We will be going back to the starting material. So for the reaction to move forward, the OET group has to leave as OET minus. Then if this is the leaving group, then we end up with the corresponding carboxylic acid. So this carboxylic acid is actually since we are using basic conditions, that will abstract this proton, and we will have a hydrolyzed product as a carboxylate anion, and ethanol is the byproduct that is formed in this particular reaction. So since it is a base catalyzed reaction, our product is going to be the carboxylate anion. So this hydrolyzed product now will have the O18 labeled one. So that means the starting ester has a O18 labeled on the carbonyl group. The product also has the O18 labeled on the carbonyl group. So there is one more way what can happen is, if we treat this with water, then the steps are going to be the same. A proton from this water molecule is abstracted by the O minus, and we end up with the OH group here, and this OH group can abstract a proton from this hydrogen. So we end up with the O minus as shown here, and which can actually lose the OH minus from this one, which is the labeled one. So what we can end up is an exchange product in which we are not having the starting ester. So the starting ester has a O18 labeled one, but the obtained product, which is the exchange product, is not having the O18. So if the reaction is stopped in between, the reaction mixture will have the labeled ester and the exchange product, which is again the starting material ester only. This is the starting material, but this is not having the O18 labeled oxygen. So basically this confirms 2 important characteristics of this particular reaction. So the first one is formation of a tetrahedral intermediate. So this tetrahedral intermediate can actually undergo reaction to give the hydrolyzed product, or this can also undergo the exchange of O18 with the solvent molecule to give the unlabeled or the oxygen from the solvent exchanged starting material. So by that we can actually confirm this reaction involves both the acyl oxygen bond cleavage and also a tetrahedral intermediate involving 2-step reaction mechanism for this ester hydrolysis reaction. This is also one of the ways by which we can confirm that the carbon oxygen, that is the acyl oxygen bond, is cleaved, because we can only explain if the acyl oxygen bond is cleaved, then the O18 labeled substance will be exchanged after the hydrolysis is over. So this is another way of confirming this particular reaction involves acyl oxygen bond cleavage. So this intermediate C can also be converted to a carboxylic acid as shown here. In this particular case, the acid is retaining the oxygen 18 labeled one. So we can explain the hydrolysis product and the carboxylic acid if both of them have the O18 labeled species is retained, then we are not so sure whether which of the bond is cleaved, it is very difficult to confirm, but this exchange product is the one which clearly shows that the acyl oxygen bond has to cleave, then only we end up with this exchanger product. So this is another way of confirming. The isotopic labeling studies also prove that the acyl oxygen bond is cleaved in this particular reaction. We can also carry out this same reaction using acidic condition. So the acidic hydrolysis of esters we will quickly go through. The reactions are very similar in all the acid catalyzed reactions. The H plus will be bonded to the oxygen because the oxygen's lone pair will be given to H plus ion. So OH bond will be formed. That is always the first step in most of the electrophilic addition reactions. Basically we say H plus is an electrophile which is added to the oxygen which is having lone pairs. So this can be, water is the medium which is used in this reaction. So oxygen is having a lone pair. This particular carbon becomes more electrophilic because the oxygen cannot have a positive charge. So this pulls the carbon oxygen bonded pi electrons towards itself. So we end up with the bond that is formed between oxygen and the electrophilic carbon. So as shown here, so this particular oxygen is now the oxonium ion having a positive charge. This is quite unstable. So this has to lose the positive charge. So what actually happens is internal transfer or the tautomerization basically happens. This leads to the shifting of proton from this water molecule to the alcohol unit. So this is the OR, which is nothing but the alkoxide unit. So this oxygen now gets the H plus ion which is shifted from the water's hydrogen. So we end up with this particular intermediate where the alcohol unit oxygen is having the positive charge. So we already know this is a very good leaving group. So when the leaving group leaves, the oxygen-hydrogen bond is shifted between the carbon and oxygen. So we end up with the loss of alcohol, and the H plus loss leads to the corresponding carboxylic acid. So this is how the acid hydrolysis reaction proceeds. So how do we know this reaction actually proceeds? Again, like the previous case, O18 labeled studies also shown here the acyl oxygen bond is cleaved. So this is one of the evidence to show this reaction also involves both the acid and the base catalyzed reaction involves acyl oxygen bond cleavage during ester hydrolysis. This reaction also, as shown here, we have a tetrahedral carbon. So this tetrahedral carbon intermediate is involved is also confirmed by the O18 studies. So the next one is unimolecular alkyl oxygen cleavage. So far what we have studied is the bimolecular acyl oxygen cleavage. But if it is a unimolecular reaction, basically the alkyl oxygen bond cleavage is possible. Let us see how the mechanism actually works. In the case of alkyl oxygen cleavage, what is the requirement is we need a stable carbocation. If a stable carbocation intermediate can be formed by the oxygen alkyl group cleavage, then that is possible. So here we have a tertiary butyl group, oxygen and this particular carbon. If this particular bond is cleaved, then we will end up with a tertiary butyl carbocation, which is a quite stable species. So when these kind of species are possible in that reaction, then the oxygen alkyl bond cleavage is possible. So another example is a triphenyl methyl group which is attached to the oxygen. When it is cleaved, we have a very stable triphenyl methyl carbocation is possible. So in these kind of cases where a carbocation, a stable carbocation is possible, can lead to the cleavage of oxygen alkyl group, and this reaction does not involve any acid or base. So this is basically a unimolecular reaction. So in this particular case, this unimolecular alkyl oxygen cleavage is possible. This can happen with both acids or base. So if it is happening in the presence of H plus ions, we say AAL1, and if it happens in the presence of base, we can say BAL1. But in both the cases, either the H plus ion or the OH minus ion is not involved in the rate determining step. The next one is the Claisen condensation. So carboxylic acid ester, when treated with sodium ethoxide in ethanol, produces a condensed product. So this is nothing but a beta keto ester. So this is the ester group, this is the alpha carbon, this is a beta carbon. So in this beta carbon we have a ketone group and we have a ester. So it is a beta keto ester. So these kind of condensed products are formed. So that's why this name reaction is a Claisen condensation reaction. So this is very similar to the aldol condensation which we have studied for aldehydes and ketones. So in both the cases, the first step is the enolate formation. The enolate anion formation is the first step. So in the case of aldols, we have a resonance structures exist between the enolate and the carbon anion. Similar to that, in the case of Claisen, we also have the enolate and the carbanion. So the difference between these two is nothing but in the case of aldol we have a proton here, in the case of Claisen we have a OET group here. So this is the only difference between these two reactions. Otherwise the mechanism and other steps are very similar. So as in the case of aldol reaction also, here also in the Claisen condensation, the second step is the nucleophilic attack of the anion on the electrophilic carbon. So this is the electrophilic carbon. So the nucleophilic anion, that is the CH2 minus anion, will attack this particular carbon. So this is how the condensation reaction proceeds. Let us study about the hydrolysis of amides. Amides can be hydrolyzed either using acids or bases to give the corresponding carboxylic acids. Amides can also be reduced. We have a couple of reduction methods. We will see one by one. Amide on treatment with lithium aluminium hydride or sodium and ethanol. It is not in the same reaction. This is condition 1, using either lithium aluminium hydride alone or sodium and ethanol alone. So these are two different conditions. They both produce amine as the final product. So the C double bond O is reduced to CH2. Amides on treatment with the P2O5 gives cyanides. Preferably this reaction is possible for the primary amides only. When a primary amide is treated with P2O5 and heating produces the nitrile or cyanides. And we also have Hofmann degradation of primary amides. So in this particular case, an amide when treated with bromine in the presence of a strong base produces a primary amine. So the difference between Hofmann degradation and the LAH or the sodium ethanol reaction is, in the case of lithium aluminium hydride or sodium ethanol reduction, the number of carbons remains the same. Here we have RC, here also we have RC. In the case of Hofmann degradation, the starting material has RC whereas the product has only R group. So there is a loss of a carbon, and this carbon is lost as a CO2 basically. So there is a one carbon loss happens in this particular reaction. Let us recap what we have studied so far. We have studied about the reactions of various acid derivatives, mainly the reactions of acid chlorides. We also did the comparison between nucleophilic addition and substitution reaction, why aldehydes and ketones react or undergo nucleophilic addition reactions whereas other acid and its derivatives undergo nucleophilic substitution reaction. We have also studied about the reactions of anhydrides and the various hydrolysis reactions of acid chlorides, esters and amides also we have studied. We also have studied about the BAC2 mechanism and the AAL1 mechanism. We have also finally studied about the Claisen condensation reaction for the formation or the preparation of beta ketoesters. With that, we conclude this session. Thank you.